The next talk is by Professor Stanislaw Janeczko, the director of the Center for Advanced Study in Warsaw. And maybe he gets the medal for the longest speech that he did to a pioneer. I'm not sure, I'll check it in the break. Thank you very much. Thank you.
Anyway, thank you very much for the invitation. I'm very happy to be here. Thank you. We now and to Cantrell. I'm very grateful. This is a great place and great event. First, I start with some to refer to the previous lecture by Professor Mina Teicher yesterday and the previous lecture by B-rationality. It was mentioned Platonic solids, and as you know, the dodecaeder is a very special, and the Plato identified it with the universe, with the cosmos. And of course, we don't know much about that, but perhaps he knew that from Pythagoras. And he, of course, mentioned beauty of that, special beauty, and this is because of that. So this is explanation. I would explain why it was so beautiful. What's beauty? What's beauty here? But you have two things flat here, and what is this? Then you can see later. And I put them here like that. It's not a very much toy for children. It's not known. Maybe this is the first time it's used here. Maybe not. But I have some cycle and use this cycle. It's me only. And then why this is so important that the dodecaeder was a cosmos, and because the beauty can join a material world and spiritual world, and this is just the let's be cosmos. So, and then this cosmos is like that, and I offer you. Thank you very much. This is the cosmos. You see, very easy explanation. And what is this geodesic there is just beauty, which is joining these two parts. This is only possible to this figure, not to others.
Thank you very much.
What I would like to say something quite fairly pictorial about invariants, affine invariants. It's a singularity part, yeah, I think, of this meeting. So about singularities, visible singularities. And if we have a cycle, then it has a center of symmetry, and of course, this is a point, as inside you know it. And then, if you perturb slightly the cycle, then this point disappears. Does not exist anymore like that you can reflect. So in such point. And then, you can just make some construction. You take parallel lines. This is in all dimensions, but I present it in the plane. You just take the two parallel lines, and then between them, you take a point P inside the curve, and just forming the function f on p phi, the ratio of these distances t and s from the point P to the parallel lines. And if you go around with angle phi of that curve, then this function makes some singular critical points, minima of quadratic or third order or fourth order and so on. And of course, if this is a cycle and you do this construction, then the infinite singularity is at the center, of course. So then there's a flat, because at that point the function is constant. So the constant function is infinitely singular in the sense of critical points. And then you see, and then this we only mark the points which are in which this function has degenerate singular point. I mean, this is degenerate singular at that point. And then it's a small example I showed here. This is this kind of curved triangle there, but of course it's told in the proposition here, but they're not necessarily calculated. And this is the construction. So if you perturb cycle, you get something like that instead of point, which might be used to construct reflection and so on. How to reflect such things like this curve with singularities? Well, this is the so another construction of the center. This is called center symmetry set. So this is a new, relatively new subject. So it's now it's quite broad, and it might be constructed as an envelope of lines of chords which join these parallel lines that points tangent points. So this is like also like that. It's another construction. That constructions are equivalent. And then examples of such center symmetry sets. So when you perturb, you see if more curved the curve is, I mean more regular, less regular, then the set is more complicated. And you see a lot of curves and swallowtails. And this is the plane. The plane is, you have only this type of things. If in the space, it's much more complicated. And then you see that this swallowtail in the first picture corresponds to some very special shape of the curve. Well, so I only show pictures today. This is. And then what happens? We have another construction, very interesting object. We call it Wigner-Berry caustic. In fact, Wigner never mentioned this as a caustic, but Berry, just Michael Berry explained how this is working, how it appears, and then his paper, he used this important object. In fact, so I show it, but so family of affine equidistance. You know geometrical optics. You know that the wave is coming and from the source. Say the source is a kind of curve, and then the distance, the wave is the same distance, so the source after some time. But that's here not that thing, but there's an affine distance. Affine distance is something different. I show you in a moment. It's not the Euclidean distance. But it looks similar. So if you have this red curve, then you have affine distance, which is this is the next curve. Then these are stages. First one, the second one already is here, but this triangle with curves is a center symmetry set. So over this center symmetry set, this affine equidistance is moving to some point, where it is just another triangle, curved triangle from the right picture, and this is this equidistant affine equidistance is expressed by this by this W lambda curve, which is just you see the linear combination with lambda. So lambda is a distance. If distance is 1/2, then this is just the curve which we call the Wigner caustic, and this is dual to the center symmetry set. In some sense, dual, of course, explain this better is maybe not this moment. Some examples of Wigner caustics looks similar, but they are really different. They they encounter a different shape, different moments of shapeless. This is important in applications for models and packing and so on. That's important, this stuff. So you see, if this is very small, if this is small cycle, then yeah. And now the shapes which were here are it's spherical shapes. Spherical shapes are a bit deformed. If we consider the spheres and the packing of spheres, this is very well-known problems that even recently. But here I want to only mention that. Then, of course, it's not the problem of packing here, which I want to consider, but problem of creating some shapes using spheres. So spherical molecules, they usually attach in some way and to have 3 points of attachment, and so on and so on, and you can build very nice, nicely looking molecule, just kind of maybe even protein modeling is from that. But usually, if there are cycles, if there are spheres, then you get rings or helices. These are periodic, of course, chains. So some chains are only like that. Then, if the sphere is a bit deformed, usually the molecules they are not so spherical. They are a bit deformed. Why they are deformed, and what is responsible for joining each? This is the case. And then only the example here with spheres. Of course, we can replace spheres by centers of spheres. And then if we replace by centers, then we get, of course, tetrahedra, which are attached to each other and then give the shapes. And usually the shapes are like that. Of course, more complicated maybe, but and this is quite interesting stuff. It's now also investigated. But with more is not spherical shape, we don't know sometimes why molecules or rather cells are attached in some way. And then there is an answer here. The responsible for that is this very internal structure of which is corresponding to the boundary of this molecule of this cell. And so then this idea is like that, for example, for the direction through the boundary of the universe reflects, like here, boundary of this molecule of this cell reflects in some very complicated structure inside. This is quite complex structure of this central symmetry set of inner caustic. Is very complicated. And then if there is a boundary of the world, it reflects in some structure of the conscience of the person, of human being. So that is maybe the people, I mean, are not so local like they think. So and then this is like that, for example, and it's easy to check if even geometrically that if this inside if this is the linear caustic and we join this way, then there are optimal joints of the cells, which looks like that. Which they are, of course, not secular. They are not secular, and this is the reason. Usually, we think that the boundary has some properties, but in fact, there's not a shape of boundary from inside. From the source of inside is important. Okay. And then let's come back to the symmetry. which is very important transformation. Here we have this picture again. We have some transformation T, which transform the points, and this is the cycle is transformed, the symmetry, central symmetry. So how to reflect points if you deform this cycle? Normally, is you take point and then in the center, if there is, you make it reflect the another point on the opposite side, and then you get just the transformation. And if the cycle is preserved, the cycle is symmetrical, it might be ellipse, might be something different. And how to do this if the center is not the center, not the point? Oh, there's another very tricky construction here. I maybe don't, there's no time to present it, but maybe slightly. So if you have such curve like down there, then if you have point, if you reflect the point in such a bit not a secular curve, you get something, some structure. This is calculation by computer. This is a program which calculates that, because this is possible to do. So, and then you see this point is just some has different properties in some way. And then we can, of course, use also the lines, chords, which can construct that that image reflection of the point. And if you have a slightly deformed ellipse, is the same. The image is maybe very small and so on, but might be very complicated. So this is the reflection. And as far as this is closer and closer to the central symmetry, then of course this is coming to the point. And some examples, if the point is on the boundary, like here on the right-hand side, then there is a kind of some other point which is radiating in some way, special way. This is the If the point is more in the center, then that gives something which is quite not related to central symmetry sets. So that's very interesting to understand the reflections of the point if from deformed spherical shape. And then symmetrization is a very interesting action of if you study the convex sets, or not necessarily convex, but sets. Convexity is also the beauty, representing the beauty, in fact. But this is, I don't want to draw beauty. So we have few methods of symmetrization, because we have a kind of object, and we prefer to have it symmetrical. How much then very complicated. So we try to symmetrize let's take ovals. This red oval is not symmetric. The parallel tangent transform. So you take each pair of parallel lines and put the interval between them to some point in the center of that interval. Then you get this blue. Is already centrally symmetric. Another symmetrization is a chord perpendicular to the line. For example, you have some line passing through this red curve, which is not absolutely not symmetric, and then you do the same, similar. You just move. These constructions are affine invariant. It's very important. All affine invariant, and you move this to the center. Symmetrization. And look what's going on. Another symmetrization is very special and never studied, I think, or I didn't find it. This is the symmetrization like that you have a point inside the curve, and you take You see this point inside the curve. And then you take all chords passing through that point, intersecting the red curve, and you move these intervals, these chords, such that that point is the center. So then, if you have the first picture, now the second picture is, you see, if you are closer to the boundary, the curve, the blue curve, is no longer stops to be convex. This is very, very special. So there is a convex soul of the convex body. That is something like that. So then you see, because this is not convex, maybe it was different interest for them. And what is this? If you consider a cycle, take some 5 minutes, no problem. If you have the cycle, this red one, then you do the same. So then you get this cycle with dotted line, dotted cycle, which is a boundary between convex and non-convex. So if you are closer to the boundary of the cycle, then you have non-convex. You see on the right picture. And this is easy to calculate, and again appear 1 over square root 2. This is very interesting. So there is a whole infinite family of cycles. So if you have one cycle, you have a family of cycles. If you have one object, you have family of objects. Usually, you have never one object. You have a family of objects. So then the cycle is here with its family, just with the rate 1 over square root, from infinity to 0. Maybe if you compactify the spaces, they're a different story. So that's quite interesting, this. And there's some calculations. Oh, well, the calculations are maybe for high school, but nevertheless, this is very interesting to have this family of cycles. And then examples depends on the structure. You see, if we are inside the curve, is a constant width curve. Constant width curves are very good because it's possible to calculate something on them. It's well parameterized curves. So that's and then you see how it's changing the symmetrization, and sometimes inflection point. If you have a convex body and no inflections, if this is changing, then coming to the inflection point, and then the inflection point is higher order and scatters into few inflection points. And this is just the case of new singularities. I mean, inflection points bifurcations. And this, and then we just, if we have such situation, then we mark the point. So there's, that's here, I showed a calculation for just for angle, 2 lines, and then you consider the point inside and calculate just this symmetrization. And this is usually the place of hyperbolic wings of that for such thing. And then you might consider also the curves like triangle and so on. Triangle has this symmetrization, you see, always is non-convex. If this is the smoothed triangle, this is better. But there's a question if there are such smooth curves which are never, which is empty set of, or empty soul, let's say, no soul. So some questions are still not answered, some are just in progress. And there is also interesting stuff. What's going on with the point of symmetrization is passing through the curve. It is passing through the curve, you get something like that. The two, this is the cycle, then you have 2 cycles which are tangent, and then here, and then the other is just the 8 kind of number. And then this is, if you perturb a bit such structure, you get this still stable, and this is just the Whitney cross-cup sections which appear here. This is the singularity known. And this is, the proposition says how it is appearing in this, in general, on the boundary, not only in cycles, in the general. And this is the sections through the cross-cup, Whitney cross-cup. You see the Whitney cross-cup on the right hand side picture, the third one, and then this is the intersection. This is exactly the family, which is after small perturbation is still equivalent to that, stable. And how to, this is the calculations here. So these calculations locally are not maybe so advanced, but they consider usually they just very highly degenerated inflection points, not the critical points like functions, but the inflection. But the inflection points is a bit more difficult to catch. But anyway, this is just the gives for that gives a new invariant. So the calculation you see, then we have a lot of this type of equation. Then we consider the local expressions by tidal series and so on, and then consider jet spaces and calculate it. So that's not. Yeah, that's some calculations. I show this. You see this third order differential. So these are very high inflection points. So just high order inflection points defined here, and it depends. In the case of surfaces, it's much more complicated. So very special inflection points there. So yeah. So we got this, and then if such point appear, then we mark the point, and then we have a new, completely new singular set inside the curve. This is the this is just the this inflection points. If appear, then we mark it. So then there's some technicalities here. For example, how to calculate find the tangent lines to this to the set of this center transformation, and there are here there are just these sets which are the points where the symmetrization has a inflection point, so start to be not convex. And you see these are completely new sets, and they of course are finally invariant, and someone might say they are beautiful. But beauty is because if we go inside, then we see what's going on in these small areas, that there are, I mean, with some orientation, this inflation points and so oriented outside of this curve is closer to boundary. The symmetrization is non-convex, but on that red, on this black curve, is convex, but with very highly degenerated inflection points. Oh. And and then there's some, of course, calculations, and also the special stable families of that, how they behave if you move the point inside. So this is just the interesting geometric invariant, I mean, affine invariant of the curves. In 3 dimensions, for surfaces, it is much more difficult. And of course, the singularities are more complicated here. But it's also some things are possible. So this is all what I want to say. I want also to finish like that. Congratulations on your new arrival, WIMSA. And I want to recall when Mina was also the statue there, yes, is Maria Skłodowska. is a Center for Studies just over, so that's very close, a few meters. And here is Mina. But next picture is, so Maria Chudnowski, who should be here, but not today, she visited recently just Maria Kigispodowska, and then there's a picture. And there's another Maria from Brazil, Maria Ruas, who's extremely nice person and efficient in organizing mathematical activity of young people, women, and not only girls or boys, but I wanted to show these people here as a very nice and very important and visionary for future. Thank you very much.
Thank you very much for this beautiful talk and for supporting women in Poland, in Ukraine, in Brazil, in Miami, international. Any questions? Yes, please.
Mine is more like symmetry is essential for that. The addition to evolution, right?
Perhaps I don't hear you. There's some symmetry.
Yeah, I mean, symmetry is everywhere in life, right? From DNA. Asymmetrization is essential for life.
Yeah, I think that's just defect of symmetry. Because of defect, I think that something might be alive. Otherwise, this is a linear and close. Now, of course, it depends on the. That if you consider the pure symmetric objects, that this is like very like model, like artificially not good word artificial, but kind of model. Then you put like real, more real. Then of course this term and so on. This spheres in the chains, which I studied many years. So then they give a lot of shapes. And also we checked how they model the DNA. And this is relatively well, I mean, in some sense, but not completely. Yeah.
Okay. Thank you very much. And we assemble again in half an hour. Enjoy.
No. Congratulations. It's very lovely.